Is it still sharing? I don't think it is. Can you see in the Zoom? Can you see the screen?
Zoom has stopped responding.
Okay. All right. I don't know why it doesn't show. Okay, I guess we can start.
I'll be talking about pseudo-random number generation. Sorry. Oh, yeah, so, I was not there.
It should work now.
Okay. Okay, so here's a brief outline of what I'll be going over. So first, like basic introduction, and then I have three algorithms for generating pseudo-random numbers, which are the middle squares method, linear congruential generator, and extra shift. So let's get into a quick introduction of like why these matter. So I guess the question I want to ask you guys is, how do computers, which are basically purely deterministic, how do they generate random numbers? And before we can talk about this, let's first see what randomness actually is and how does it show up. So nature has a bunch of random fluctuations. There's like the rate of radioactive decay, the number of faces on a random pebble you pick up, thermal noise, and just a ton of other things that are really hard to measure and are pretty much random. And it is impossible, or it is possible in theory to measure one of these random events. Like say you have a sample of uranium and you measure how fast it decays. You can technically use that to create a random number by mapping it to something, but it poses some issues when it comes to scalability and speed, because if you want to generate a bunch of random numbers for a simulation, you can't really just stare at some uranium and wait for it to decay. So that allows us to turn to pseudo-random numbers, where we use algorithms to generate these numbers to have, I guess, random numbers whenever you want. So a pseudo-random number is defined as a number that appears to be statistically random despite having been produced by a completely deterministic and repeatable process. Basically, what that means is when you first look at a pseudo-random number and you look at a few of them, they look random enough, but when you kind of, I guess, look at the pattern between them, you often see that they aren't really random. And there's a good way to visualize this using a random walk visualization, which shows the projection and relation between a set of generated numbers by plotting distance between some consecutive numbers in the set. And so this is a truly random visualization. And I forgot exactly how this was measured, but these numbers are random from each other. And you can see that there isn't really any set like relation between them. Sure, there's a bunch of numbers that are like clustered here, but based on one number, you can't really see that there's a pattern going to the next one. But if we look at a pseudo-random visualization, you can see there's a very obvious pattern. It's mirrored along this axis, and it tends to repeat after some time. And just comparing the two charts, you can definitely see that one is a lot more random and a lot less uniform than the other. So let's get into some methods to generate these pseudo-random numbers. The first one that I like to talk about is the middle squares method, made by John von Neumann in the 1940s. And the way this works is you start by choosing a seed number. So when I was making this presentation, the last 3 digits of Unix time were 186. So I just chose that as our seed. And now what you do is you square this number and select the middle digits that you want as your next number. So I wanted to generate 3-digit random numbers. So after squaring 186, you get 34596, which means our middle numbers are 459, and that's our next number. So you repeat this number, or you repeat this as many times as you want. And eventually doing this, you get 459, then 68, then 624, then 937, 796, and so on. And this is really great if you want to generate a bunch of random numbers quickly. But there is one, I guess, downside, which I kind of mentioned earlier, is that once you get a repeat number, it's kind of easy to see that the cycle is going to start all over again from that repeat number. And that's just kind of something you have to deal with for pseudo-random numbers because they are generated by algorithms. You can't really avoid repeats. And this is known as the period, and some seeds will inevitably have a longer period than others, and you kind of just have to see if you get lucky. So here's the linear congruential generator, which I'll call the LCG. And this is another relatively simple pseudo-random number generator, and it uses this formula. So xn plus 1, which is your next random number, is generated by multiplying your seed by a, which is a multiplier, and adding c, which is just used to avoid repeats, and taking it modulo n. So yeah, that's kind of a basis of what each thing is. And we are assuming everything is non-zero because obviously if some of them are zero, that tends to make things complicated. So let's try this with a completely arbitrary example. So I chose m is 79, a is 43, c is 15, and our starting seed is 21. So let's just go through these. So if you start x1 is 43 times 21 plus 15, all modulo 79, which gets you 63. Then using 63 to generate our second random number, you get 9. Using that to generate the next one, you get 7, and so on. So the list that you get using these parameters is 21, 63, 9, 7, 0, 15, 34. And you can see there's not really any pattern between those, but actually the next term after 34 is 7. So it does repeat after that. And like I said, you just kind of have to hope you get lucky. But yeah, so this is also relatively great for generating numbers. And finally, let's get to the last one, which is kind of the most complicated one, but also one that's used a lot more, is extra shift. And the general process for this is relatively simple. So you take a seed number and convert that to binary. Then you perform a bit shift either left or right, and kind of any arbitrary amount you want. Then you perform the XOR operation on the numbers in steps 1 and 2, and I'll get to that in a bit and just explain how it works. And then you just repeat these steps as many times as you want, but I would repeat the direction of the bit shift each time. You don't technically have to, but again, it just makes things more random. And finally, once you've done that as many times as you want, you convert the final number back to decimal, and there's your random number. So I chose the random number 3146505, just why not? And you start by converting it to binary, so that's that number right there. And then you take your left shift 13, which ends up making most of these 0 and some of these are 1s. So then you do the XOR, I guess, algorithm or operator. And the way that works is you basically compare any two numbers. If these two are the same, then you put a 0. If these two are different, you put a 1. So by doing that, you get this next number, and then you just repeat that again. So first of all, I did a left shift 13, then I did a right shift 17, and then the left shift by 5. And by doing this over and over again, you eventually arrive at this final number here. And I guess I'll just sum that up in a small table. So you start off with 3146505. By doing the first XOR operator, you get 40579969. Then you do it again, you get 405897993. And you do that again, you get 676562217. And you could use all of these numbers as your next random number, or you could just use the last one. It really depends how, I guess, strict you want to make the bounds for your randomness. And yeah, so that is the final number we arrive at after using XOR shift 3 times with these random numbers. And so just for a quick summary, middle squares, LCG, and XOR shift are all 3 fairly simple pseudo-random number generation algorithms. You can see that they're all not too difficult to implement in code. And because of that, all 3 of them can be completed in constant time, which also makes them very good for real-time number generation. And it's also not too difficult to, I guess, perform. The problem with these are that none of them are great for cryptographic purposes, because if you have the seed, you can kind of arrive at everything else, which means, you know, if you're trying to like encrypt your computer or encrypt a file, it's not really the best idea. So in actual industry, cryptography often uses things like entropy pools, block ciphers, and sometimes even using the truly random numbers from physical processes. Like I was looking at one that actually looks at uranium and sees how fast it decays, and then uses that to start off a seed and then do some other processes to get really, really random numbers that can't be found. And obviously that takes a lot more computation, it takes a lot more effort. So for our purposes, often not needed, these algorithms just tend to work. So yeah, any questions?
Where did the like 17, 13, and 5 something?
Random. I just came up with them. You can choose pretty much whatever.
But like you can have it be like fixed, like you just like choose any set of numbers and it'll always just work.
I believe so, yeah.
Is the algorithm like, how do you decide like, how many times you do the random algorithm? Is that as much as you want? It's wait, it's like, instantly set an amount or like you have there?
I mean, like I said, none of these algorithms are really industry standard because they're not secure. So it's really just you kind of have to do a trade-off of how random do you want it versus how much computation power you have. So if you really care about it being random, then do it more. If you don't care and you're just doing it for like a class project, you can just do it once. Did you have a question? Sure. Yeah.
I think the simple plus boost why we're using source something. It's like, it's just standard to see it, they're not different from next time stamp.
Yeah.
We never use random numbers.
Yep. Yeah, so any other questions or so? Thank you guys.
You know how to, okay, whatever, I'll keep it here. Okay, so I'll be talking about dynamics and chaos. So this is some introductory chaos theory. Okay.
You might have to like click on the presentation. Like with the mouse. I'm pretty sure it's just like keyboard input.
Okay. So here's the outline. First, I'll give a motivating example, then I'll give some theory to like mostly definitions and stuff. And then I'll talk about these two things called the diagonal exponent and then bifurcation. And then we'll look at two classic examples, one being the Dan-Griffin pendulum and one being the logistic map. So first, I'll give a motivating example. So we have this Newton's second law for a Dan-Griffin pendulum. So this comes from physics, not very important. And then what matters most is the expression down here. Oh, oops. Wait, what happened? Okay, what matters most is the expression down here, which is what we'll be using in future slides. So basically, this is the second order term, this is first order term, and this is some nonlinear term, and then this is a driving force. And then in some introductory physics classes, we usually use small angle approximation. So sine theta is approximately theta. And then we will replace the last term on the left-hand side with just theta. And then we know that we can solve this differential equation pretty easily. And it will give a transient solution that depends on initial conditions and a steady state solution that does not depend on initial conditions. So, but it motivates the question, right? What happens if we use sine theta instead of theta in the original equation? Then will we still get this behavior where we have a transient solution dependent on initial conditions and a steady state solution that does not depend on initial conditions? And it turns out that obviously because I'm making this talk that this is not true. Otherwise, I will not be here. So we'll see that this is actually replacing this theta here with a sine theta actually complicates matters. So here's some formal definitions and theorems. So we have XC is a metric space, F is a function from X to X. Then a fixed point, X in X is a point such that F of X is equal to X. So applying a map on X does not change X. A periodic point is a point such that there exists n in natural numbers such that the nth iterate of f of x is equal to x. So this basically means applying the map f some number of times gets you back to where you started. And the least n is called the prime period. And the orbit of x under f, denoted O sub f of x, is a sequence f of x and dot 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 where each term in the sequence is generated by applying a map on the previous term. And this is the case if f is not invertible. Otherwise, if f is invertible, we take this sequence instead. So this sequence is basically the previous sequence, but you also include all the pre-image of all orders. So basically, what a pre-image, yeah, go ahead.
I don't know what a metric space is. Can you explain that?
Oh yeah, so metric space is just, it's just any, so a metric space X comma D just means it's a set X equipped with some metric D. So a metric is basically a notion of distance that applies between any two elements in the set X. So if you don't know what a metric space is, you can just kind of replace this with, for example, the real line with the standard Euclidean distance, or the space Rn with the standard Euclidean distance. It's basically the same thing. It's just more important. Okay. Yeah. So we say this map exhibits sensitive dependence on initial conditions if there exists delta greater than 0, such that for any x and epsilon greater than 0, there exists y in x and in natural numbers such that 1, x is not equal to y, 2, distance. So again, if you're unfamiliar with metric spaces, you can replace this d here with just absolute value of x minus y. The distance between x and y is less than delta, and it's less than epsilon, and the distance between the nth iterate of x and the nth iterate of y is greater than or equal to delta. So what this is saying is that there's this some number, which is delta here, that for each element in the set, and for each element in the set, we can take an epsilon neighborhood of the element. So an epsilon neighborhood is basically all elements in the set that are within some very small distance of this element x here. You take an epsilon neighborhood of the element, and then in every epsilon neighborhood, there exists another element that is different from x, right? So x is not equal to y, such that there is some n, so that the nth iterate of x and the nth iterate of y is actually apart from each other by some value greater than this delta. So a remark is that if a system possesses sensitive dependence, then numerical computation becomes invalid, because to do numerical computation, you always have to make some estimates. Right? It's always an estimate, where it's like this computer only have so many degrees of accuracy, so many digits of accuracy. So it's gonna inherently diverge from the actual orbit. So another definition is f is topologically transitive if there exists x in the metric space, so that the orbit of x is dense in x. So what dense means is that for any open set in x, you have the orbit will intersect it somewhere. Okay, and we have a proposition that basically so this proposition gives a more practical formulation for what it means to be topologically transitive. It states that if x has no isolated points, that's just a technicality, we don't really care. And f is continuous, which is also just a technicality. Everything we'll be working with here will be continuous. Then f is topologically transitive if and only if for any two non-empty sets u, v in x, there exists n in natural numbers such that the nth iterate of f applied on u intersection v is not equal to empty. So what this means is that you just take any two subsets of x, and then apply, and then we can guarantee that if you apply f on one of the subsets for some number of times, then it's eventually going to intersect v. It's essentially going to intersect the others. Eventually going to intersect the other subset somewhere. For the proof is optional. I will skip this right now. We'll come back to it later if we have time. But note that the reverse direction is obvious. And I'll also show this if we have time, but I'll come back to it. Yeah. Okay, another definition is if f is continuous, then we call f is chaotic. If and only if it is topologically transitive and its periodic points are dense. So notice that it is an if statement. So wait, actually, what am I saying? It's just, okay, it's if and only. This F is chaotic if and only if it is topologically transitive and periodic points are dense. And we have a theorem that says chaotic maps are dense. Chaotic maps exhibit sensitive dependence on initial conditions. Unless the entire space consists of a single periodic point, single periodic orbit. So what this is saying is that if you have something, if you have a map that is continuous and it is topologically transitive and periodic points are dense, then we automatically get sensitive dependence on initial conditions for free. And remark is that converse is not true. So if you have sensitive dependence on initial conditions, it might not be chaotic. And the common misunderstanding is that chaotic is equivalent to sensitive dependence, which is by this definition is not true. Okay, again, I have proof of theorem here, but we'll skip this and we'll come back if we have time. Okay, first of all, does the definition make sense to everyone? So there's three definitions. There's actually there's just two definitions. There's one for chaotic and one for topological transitivity. Go ahead.
Is there any way you can explain like what it means to be topologically transitive in like a little bit like less abstract way? I like don't. But I don't really get like the dense part.
Yeah, so we can use the composition here. This is an alternative formulation for.
Okay.
Does this make sense? So
Yeah.
you take any two subsets of X, call them UB, and then we guarantee that if you apply F some number of times to one of the subsets U, then you guarantee that it will intersect B.
Okay.
Yes.
So it's like saying the nth map of a subset will always intersect some other subset of the original set.
Yeah.
Okay.
And it's for any other subset.
Yeah, any other.
Yeah.
If the same subset would that also work?
Sorry?
If it's the same subset.
Well, yeah, you can.
Yeah, well then you can just take
Yeah, you can do your own, right?
yeah,
Oh,
sure.
yeah.
So yeah, we can let's say U is not included. Okay. Okay, so here we have an example of a chaotic map. So consider, and this is in R2 for you, or R1 actually. So you can ignore all the metric space.
Okay.
Nonsense. Okay. And consider F maps from -2 to 2. Maps -2 to 2 to -2 to 2. And then this is the function here. So kind of what this does. Let me pull up Desmos here.
Yep.
Okay. Kind of what this means is that turn off these. So this is the original mapping, right? This is 2x absolute value, 2 times absolute value of x minus 2. So this is just like a V shape here. And we're only considering the box -2 to 2 on -2 to 2. So we're only considering this area here, right?
Yeah.
This area here. And then let's look at what the. So if you apply F 2 times, you get this. And if you apply F 3 times, you get something like this. So kind of what's happening here is that you can see for the nth order, it will essentially just oscillate faster and faster between 2 and -2. So that's just qualitatively what's happening. Like yeah. So this makes sense. And then, for example, third order will be just even like more oscillations, I guess. So you can see there are, for example, there are 8 oscillations in total here, and 4, yeah. Okay, with that in mind, let's try to think of why it is chaotic. probably also true. So just a reminder of what's going on. You have essentially with many iterations of the maps, you get something that's like this. And it's like it's gonna oscillate many times in between -2 and 2. So first, let's think of why this thing is dense. Why periodic points are dense. We claim that we can always find a subinterval I of length 1/2 to the n-2, such that f of n, the nth iterative of f applied to I is equal to -2. It's equal to the interval -2 to 2. So what this means is that you can, as n increases, oscillations get faster, and you can eventually find some, like for any, let's say, this is 1/2 to -n-2, I guess. And then in this small region on X, the graph will go from -2 to 2. And this is important because then this means that f of the nth iterative of f has a fixed point on I. Why is this true? For example, consider this is -2. This is. Can anyone see this, by the way?
Yeah.
Right. And then we consider some small interval here, right? And it's gonna go from -2 to 2 on the y. Or yeah, like this. So why does this have a fixed point on I here? Because if we consider diagonal, right, this will just be y equals x. Then we see that it will cross the diagonal somewhere, right? It'll cross the diagonal somewhere. So at this point will just be the fixed point. Does this make sense?
So how does it prove like it's dense?
Okay, it proves that it's dense because you can essentially take intervals of smaller and smaller size, right? The subinterval of I is of length 1/2 to the n-2.
Yeah.
So essentially, if you increase n, this interval size will become smaller and smaller.
Okay.
So you can show that. For any interval of any size, there will be a fixed point because you can just take the next smallest negative power of 2 and apply this region.
Okay.
Yeah. So we also need to show topological transitivity. So it's almost the same reasoning. So for any u, and so for any subinterval u on -2 to 2, there exists n in natural numbers such that the nth iterative of f applied to u is equal to -2 to 2. So what this means is that for any subinterval, if you apply the map enough times, then you will always map to -2 to 2. So this is also because as n increases, it oscillates faster and faster. So at some point, the subinterval, it will oscillate so fast that any subinterval u you take, there will be another subinterval of u from -2 to 2. That maps from -2 to 2. So since there exists n such that nth iterative of u maps from -2 to 2, then we can take any subset B or any subset B of -2 to 2, and the nth iterative of f of u intersect B will be non-zero because this is already -2 to 2, and then any subset of -2 to 2 will intersect -2 to 2. Okay, so now let's talk about something that's called the diagonal exploit. So again, we have some function f, and Oh wait, to motivate this, first of all, let's go back a little bit. So F is so we know that if we know that chaotic maps exhibit sensitive dependence on initial conditions. But it's often hard to show, it's often hard to figure out if something is chaotic directly. So the Lyapunov exponent gives a good indication of when something might be chaotic. Or when something might be chaotic. And so here's the definition. You have function f and xy be initial points in the phase space. Then the separation vector delta of n is given by delta of n equals the nth iterative of f of x minus the nth iterative of f of y. So this is basically the image of x and the image of y, each on after applying f n times. And the Lyapunov exponent lambda is given by the limit as n goes to infinity and the limit as the magnitude of delta 0 goes to 0 of n minus 1 of 1 over n times ln of this thing. And continuous system, the case for continuous system is almost exactly the same here. You can kind of think of it as use t instead of n, because t is just continuous system. You can think of it as many small chunks of discreteness, I guess. And then t plays a similar role as n. And then intuitively, here's what it means. Is that for some delta, that is the difference between two initial states, you apply f n times to x plus delta and x, then this difference will be approximately equal to delta times e to the lambda times n, where lambda is the Lyapunov exponent. And this is for n large. So this is saying that after you apply f many times, the distance will kind of grow exponentially. Yeah, so this measures the rate at which two initially extremely close states grow over time. And then, yeah, so if it's greater than 0, it grows over time. And then this is a good indication of chaotic system. So if you look back at this, you see here that if delta, like roughly speaking, if delta of n grows anything that's sub-exponential, then this thing will probably go to 0. And also if it decreases, then obviously like it's probably negative. But if delta of n grows faster than exponential, then this thing will be greater than 1. Or greater than 0 actually. Well, in which case it will be a good indication for chaotic system. So an important remark about the Lyapunov exponent is that it doesn't necessarily imply chaos. It is just a good indication of chaos. You need additional information to prove that it's actually chaos. Okay, yeah, we don't care about this. Okay. Okay, so this is a more practical way of how you compute that Lyapunov exponent. So instead of the limit definition, you do something like this. Yeah, so we just do a bunch of math. So essentially we have this thing we have earlier. We have this thing from earlier, right? And then you can isolate delta, you can isolate lambda like this. And then you can take delta goes to 0, right? As from the definition. And then I'll use definition of derivative to get this. And then notice here that this thing inside the natural log is the derivative of the nth iterative of f. So you can use chain rule to expand it out like this. And then this just packages into a summation. And then you can substitute in and then make more simplifications to arrive at this. And this is really helpful because what is x? Because x of I is the image after I iterations of f. So you can essentially compute. You can keep applying f and then keep recording what the image is, and then at the end you like try to sum up everything, and then like for a sufficiently large number of iterations you do, you can get like the lab of exponent to some degree. Okay, here's an example of how here's a simple example of how this thing can be computed on a very simple map. So consider S is the unit circle in 2D, basically. And then we're considering the doubling map on the unit circle. So what that means is that on the unit circle, every point is defined by its angle, right? And then the doubling map basically doubles the angle modulo 2 pi. So if you have, let's say if you have pi over 2, the angle is pi over 2, it maps to pi. If angle is pi over 4, it maps to pi over 2. And then there's this continuity at theta equals pi. Because if it's at pi, then it maps to 2 pi, which mod 2 pi is 0. So derivative kind of looks something like like this. So this is slope 2, and then this continuity and slope 2. And then what's interesting here is that it doesn't matter where you are. The derivative is always 2. So you can put that in, and then it just becomes ln2. And then this thing is just the 1 over n and sigma from summing from I equals 0 to n is just basically taking average. But it's always ln2. So the average is ln2, which is greater than 0. Wait, that's even greater than 0. It is, yeah. Wait. Crap, is that greater than 0? It's less than 0.
Wait, no, it's greater than 0.
Wait.
It's like 0 point something, right?
It's 0.69313.
If it's less than 1, wait.
Oh yeah, if it's less than 1. Yeah, so this is greater than 0. This is greater than I'm size is correct. This is greater than 0.
Alright.
Okay, so this means that this doubling map has sensitive dependence on it. Right, because we said earlier that if it's greater than 0, then this has sensitive dependence on initial condition. Because it grows exponentially. And it's pretty easy to show that it grows faster than exponential than its sensitive dependence on it. Let's talk about something called bifurcation. So first, definition, a fixed point is attracting. Wait, hold on. Yeah, okay. Fixed point is attracting. If there's this constant in between 0 and 1, an open interval containing the fixed point, such that in any the image of any point x in the interval and the fixed point is less than the distance between the point x and the. So this is basically saying it's getting you apply the map and it's getting closer. It's getting you take any point in the interval, you apply a map to it, and it gets closer to the fixed point. And similarly, it is unstable. The fixed point is unstable or repelling if you take any point, you apply a map to it, and it gets further from the fixed point. And a periodic point is attracting or repelling if it's attracting or repelling fixed point of the nth iterative of that. So basically, you're considering a fixed point of f to the n. Does this make sense? This is pretty intuitive, right? It's more intuitive than perhaps earlier definition. Okay, so here is how we can practically decide if something is attracting or repelling. So let's say f is differentiable, just to make it nice, at the fixed point. And then we denote a as the derivative, absolute value of the derivative at the fixed point. Then the fixed point is attracting if a is less than 1, and if and only if a is less than 1, and repelling if and only if a is greater than 1. So basically you take derivative, and then if it's less than 1, like everything around it converges, everything around the fixed point converges to the fixed point. And if it's greater than 1, everything around the fixed point goes further away from the fixed point. Proof is just you apply definition of derivative and you not very interesting. Okay. So here's a sufficient condition for when we know that bifurcations will not exist. Wait. Okay, I should probably say what a family of functions means. So this f sub lambda is a family of functions. What does that mean? It means that f is some kind of map, and then the map depends on this one parameter called lambda. So basically, we'll see later, for example, when we consider logistic map, that logistic map f of x is given by mu times x of 1 minus x. So here, this is a function of x, and with one single parameter mu. So this is kind of what the family of functions mean. So instead of the single parameter will be lambda in this case. I've noted lambda. Yeah, I think it's best if I'm just copy. To be honest. Okay, are you guys interested in this? Do you guys for sufficient condition for no bifurcation? Okay, I'll just talk through it briefly. Suppose that you have a fixed point, x naught, and then at this fixed point, the derivative is not equal to 1. Then basically this is saying that as you for some neighborhood of lambda naught where this fixed point exists, then for any lambda in that neighborhood, there's gonna be no bifurcation. So bifurcation basically means that the behavior of the map will change. So this is basically saying that like everything will act the same for any parameter in this interval, in some interval. And then proof is just you apply implicit function theorem on this thing control, and it's like not very interesting. Okay. I'll come back to this after the demo. I think the demo will illustrate very well what this is. Yeah, so let's now return to depth-driven pendulum. Return to something practical besides from all the theory nonsense. So again, we have this thing from Newton's second law. And then we first talk about this type of bifurcation called symmetry breaking bifurcation. So what is symmetry? Symmetry means that, so first you can observe from this equation that if you take a transformation, theta goes to minus theta and t goes to t minus pi over omega, where omega is the driving frequency. Then if theta 1 is a solution, then theta 2 under this transformation is also another solution. So basically what this means is that you take pendulum, and then so it means that it doesn't matter what side of the pendulum you're on. So for example, you take pendulum, and then you could say you call this side the positive side, and you call this side the negative side, or for the angle, right? For the angle theta. And what this is saying is that it doesn't matter that the two sides are symmetric. Like it doesn't matter what side you find to be the positive side. Yeah, so that's symmetry. If theta 1 is equal to theta 2. So like if you just change the sides, it's basically the same thing. But if it's not, then we say that spontaneous symmetry breaking has occurred. So now let's do the demo. This, oh, okay. This is, yeah, this should. No module called matplotlib. Wait, what? Does anyone know how to fix this? No, wait.
So not
Wait, no, it was running earlier. No, it's just, wait, what the? Oh, maybe it's glitched. I'll just like, wait, no, it's still like giving error. Frick. Well, what's the command? I don't really know command. No, I was not. I was just using this. Wait, I have this installed though.
PIP space install space matplotlib.
What the hell? Okay, yeah, this is cooked. Oh my god. Let's go back to slides first. Okay, yeah, so at this point, at Q is basically this parameter here, right? This is we're varying this parameter. So this system actually has three parameters. It has Q, S, which is something to do with damping, and it has F, which is the amplitude for the for the driver, and omega, which is the driving frequency. So we're holding the F and omega constant, and we're changing Q here. So at Q is equal to, it's around this value, symmetry is broken. So if Q is less than this value, then the asymptotic solutions are symmetric. So it doesn't matter if it's right side or left side you define as positive, it will be the same thing. But for Q is greater than this value, there are actually two asymmetric asymptotic solutions. So depending on which side you start on, you converge to something, you converge to different things, basically. You converge to different limit cycles. So let's see if that's finished installing. Here's a hat. Okay, good. This is for Q less than the bifurcation point. So now you can see that they're both they both converge to the same thing. But here I'll show you what happens when you say Q is greater than the value. It will split to two things. So here we change Q to like 1.25 and it will break symmetry. There. So we have this red one and a blue one. So it depends on which side of the vertical you start on, you converge to two different Lehman cycles. All right, pure doubling, again, demo. Okay. So what pure doubling means is that the limits, the period for the limit cycle, which is basically how many iterates of the function f you need to run in order to get back to the original point, the period will double in some certain place. So let's plot this at Okay, so this is period 2. You can see there's like kind of like two different trajectories here. That's how we kind of see it period 2. It goes around 360 and then it kind of goes the other path and it goes around 360 again, and then you go back to the same thing. But if you change the value to something larger, you get more periods. You get larger periods. Let's do, what value did I have earlier? 0.7. Okay, let's do 0.76 probably. Yeah, so now you can see there's way more periods. I think this is period 8 at least, right? So there's 2 here on the innermost one, and then there's another 2 here, and then there's 2 more here, and then finally 2 more on the outside. So this is period 8. So kind of what this means is that as you increase Q, you need to apply F more times to get back to the solution. Or like the length of the cycle is longer. Yeah. Now this room is so big. Okay, so here's the bifurcation diagram I drew. Very sloppy code, right? Like you can see this here, it's like not very precise, but qualitatively this is what's happening. As you increase Q, you get more and more. The period increases. For example, at around, I think, yeah, at around this point, period increases, and then so it becomes period probably period 4 here, and then around this point, period increases again, becomes period 8, and then it becomes, and the period doubles faster and faster. Okay, I think we're pretty much out of time, but this is another very classic example. You should definitely look at the slides for this. Yeah, so this is another example of period doubling. So I think all the bifurcations for this map are period doubling. And yeah, so what's most interesting about this period doubling is that this guy called Feigenbaum actually shows that if you take the ratio between any 2 bifurcation points, it actually converges to a single value. It actually converges, right? And then the constant is like this thing called the Feigenbaum constant, and it's delta given by 4.669 something. And it's given by this sequence OEIS, if you want to write it. Yeah, and this constant is actually proven to be universal for all 1D maps with single locally quadratic maps. So you'll find out what that means if you look at the logistic maps. But it just basically means that for a lot of maps, for a lot of 1D maps, you have the ratio for the bifurcation points is actually constant, and it's invariant. Okay. All right, let's get out of here, guys.